Hey everyone, I'm Adam Dede and welcome to Neurojournal Club. Today we're going to be talking about how do hallucinogens change color vision. So the reason for talking about how hallucinogens change color vision is that this is one of the most commonly reported effects of hallucinogenic drugs. People report seeing things that are not actually there, and they also report having changes in the way that color is experienced. Specifically, they seem to talk about the idea that color is actually brighter or more vibrant or more easily differentiated in the hallucinogenic state. But is it really? So first, let's just take a look at what it is that people feel like they're experiencing. So here's a quote from Huxley, 1956. "Heaven and hell. First and most important is the experience of light. Everything seen from those who visit the mind's antipodes is brilliantly illuminated and seems to shine from within. All colors are intensified to a pitch far beyond anything seen in the normal state, and at the same time the mind's capacity for recognizing fine distinctions of tone and hue is notably heightened." So Huxley's kind of summing all of this up into a really powerful paragraph here. The idea that colors are intense, and not only are they experienced as intense, but they are actually related to what's going on in the outside world. Like you're experiencing something that's more real than reality. And if you remember in the last video, we talked about how people who were on DMT had one of their key experiences was that the reality they experienced on DMT seemed to them more real than regular sober reality. So today we're going to take a look at a study from Hartman and Hollister in 1963, so we're really hearkening way back, but it turns out people have been looking at the effects of hallucinogenic drugs on cognition for a pretty long time, and some of these older studies are pretty cool. So let's take a look at what they did. So they had 18 participants. All participants took all the drugs, and they had them take psilocybin, mescaline, and LSD. So basically the way they would do this on different experimental sessions, because you can't have people take all three of these drugs at once, but on different experimental sessions, they'd have people come in, and they'd first test their ability to do various things with color. We'll talk about what things they had them do. And then they'd give them the drug. They'd wait about an hour and a half or so to make sure that the drug had really hit, and then they'd retest them on those same tests of color perception. Okay, so what did they do? So the first task that they had participants do was this hue discrimination task. And so here what I'm showing you is just an example of me going through and doing a little bit of this kind of hue discrimination type thing on an online task. I've linked it down below if you want to take a look at it and try it yourself. This isn't exactly the same way that Hartman and Hollister tested it. They tested it physically. This is 1963, with little buttons that had different colors on them. But essentially, this is roughly the same task. And so let's take a look at what they found. So here on this graph, we're looking at errors on the y-axis. And we can see the group that took LSD, when they took mescaline, and when they took psilocybin. And in blue, we're looking at the number of errors that they made before they took the drug, and then in orange, we're looking at the number of errors that they made after they took the drug. So the thing that jumps out at you here is that all three of these drugs, LSD, mescaline, and psilocybin, they all cause an increase in the number of errors in hue discrimination. So contrary to Huxley's claim, and indeed the claim that a lot of people have made when they're on these hallucinogenic drugs, that colors seem sharper and that they feel they have a better ability to discriminate hues, these participants are actually exhibiting a decreased ability to discriminate hues. So something is going on that's really weird here, where there's a perception of having better hue discrimination, but in actuality, hue discrimination has gotten worse. So what else did Hartman and Hollister take a look at? So here what we're looking at is a quickly spinning black and white disc. And here, if I just pause it for a second, you can see that it is indeed just black and white. Now, as I let it go again and it spins really fast, try and look right in the middle of it and try and determine if any part of it looks as if it has a color other than just black and white. So when Hartman and Hollister exposed people on hallucinogenic drugs to these types of flickering black and white discs, what did those people report in terms of their perceived colors? So here we're going to take a look at black and white flicker-induced colors. So they're looking at discs spinning just the same as the type of disc that you just looked at. And on the y-axis here, we're looking at perceived colors, so the number of different colors that the participants reported when they're looking at these spinning discs. And you can see that before the participants take the drugs, they're reporting about 4 colors. But we see a dramatic jump in the number of colors that these participants are experiencing after they take the drugs. So something's going on where they do have this really strong experience of having a lot more colors in their world than before they took the drug. And that fits with the subjective experience that people have reported before. Now, one thing that was kind of interesting that Hartman and Hollister took a look at was the relationship between the reporting of more colors during this flicker task and the errors that people made during the hue discrimination task. Now, what I've done here is just take some data from their original report and kind of replot it in a way that kind of highlights this relationship. And what we're looking at here on the x-axis is the frequency of reporting a color, and on the y-axis we're looking at the errors in discriminating a color. So if we split color space into red to yellow, yellow to green, green to blue, blue to violet, violet to red, and make a different point for each of those areas in color space, then we can see that there ends up being a relationship where the more often that a particular area in color space is reported when participants are hallucinating that color as they look at the flickering black and white disc, that same area of color space turns out to be an area of color space that the participants are particularly deficient at being able to discriminate when they're looking at that color in actual fact. So colors hallucinated are colors unseen. It's as if the system can either see the color from internally generated sources or it can see the color from externally generated sources, but it can't manage to see that color from both sources at the same time. So that's kind of a cool thing, that there may be this kind of either or on access to consciousness. And here is where Hartman and Hollister highlight this effect themselves. They talk about ranking both sets of measures from high to low across areas of red-yellow, yellow-green, green-blue, blue-purple, and purple-red-blue, or purple-red-purple. Correlations were negative 0.6, negative 0.9, and negative 0.9 for LSD, mescaline, and psilocybin, respectively. Now, those are some really strong correlation values, and sadly, in 1963, a lot of stuff was reported in tables rather than being reported in figures. So we can't actually take a look at what the data exactly were that they plotted to be able to get this super strong correlation value. It seems a little bit spurious to me, so I'm just going to kind of point that out to you, that when I kind of pulled data from their paper, from their tables, and replotted it, I got this, and this is the figure that we just looked at. Now, it does look like there's a relationship where the more often that a color is reported, the more often that same color has a problem in discrimination. But it doesn't really look like we're looking at such crazy strong correlation values as they're reporting. So I'm not exactly sure how they binned their data specifically. There were a lot of choices under the hood on how to bin that data in order to do this analysis. But just a grain of salt there, that these correlation values, 0.6, 0.9, and 0.9, those are kind of really high. So it makes me a little bit worried to put too much on that. And then the last thing that Hartman and Hollister looked at was synesthesia, so colors seen when tones heard. So to elicit this, it was super simple. They just played pure tones to people, so just kind of like a beep, and then asked, what kind of colors do you see when you hear that beep? And unsurprisingly, before the participants took the drugs, in blue here, we can see that they didn't perceive a whole lot of colors. But then after they took the drugs, we see a sudden jump up that for LSD, mescaline, and psilocybin, all of the participants are experiencing a sudden increase in synesthesia, the tendency to have experiences bleed across the borders between different sensory modalities. So they're hearing these tones, and it's causing them to see colors. Pretty crazy. All right, so what conclusions can we draw from a study like this? So drug users not as good at color vision as they think. So if you're tripping and you think that the world is suddenly brighter and sharper and more detailed than it ever was before, well, that might just be in your head. Could be a fun experience, but don't start thinking you're a superhero. Worse color discrimination. So that was the big finding here, was that the participants on the drugs actually got worse at being able to just tell the difference between one color and another and put them in order. More color perception, though. This is where the dichotomy comes in, that while the participants are having a lot of trouble discriminating between colors that are physically in front of them, they're actually seeing and perceiving more colors in the drug state than when they're sober. So there's a weird trade-off going on where more perception actually is making them less able to perceive the actual world. Colors perceived are the very colors they cannot discriminate. So this was that direct relationship that we saw between colors that got perceived when looking at the flickering black and white disc were the same colors that the participants couldn't discriminate when they were trying to put them in order. So something's going on here where you can either have input to consciousness from the external world via the sense organs, via the eyes in this case, or you can have an input to consciousness from an internally generated source, a hallucination. And it seems to be the case that consciousness can only receive from one of these sources at a time, because the colors that are being perceived during the black and white flicker, those ones that are being, maybe you could say, hallucinated, are exactly the colors that the participants can't perceive when they're looking at them in actual fact. So this is kind of a weird thing going on, like how things fight for access to conscious workspace when that seems to be a limited resource. Only a certain amount of stuff is going to get into consciousness. So some limitations and some questions. So how do other states of consciousness alter perception? So here we're looking at this drug state, seems to cause this decrease in color perception, decrease in color discrimination, I should say, but an increase in perceived colors. But how do other states alter conscious perception? So that'd be an interesting thing to take a look at. Okay, and then the next question, how does the state of consciousness interact with content? So the question here is about how does the state that you're in determine what information is able to make it into the conscious space. If you only have a limited amount of resources to devote to processing of anything that happens to be in front of you or in your mind, how does the state that consciousness is in, maybe your mood, your drug state, how tired you are, how awake you are, how excited you are, how does this mood or state, how does that change what information makes it into consciousness? It'd be really interesting to know exactly how that interaction takes place. And then the one big limitation that I just want to have you keep in mind here is that correlation analysis, as we talked about before, it seemed to be just kind of weirdly strong, and it's kind of hard to poke under the hood here just because 1963 things weren't completely reported in as much detail as you might want, and of course the authors are no longer active in science, so can't really send them an email. Anyway, that's the video for today. I'm Adam Dede. This has been Neurojournal Club. If you like the video, please click the thumbs up. Please go ahead and subscribe, and you can click the link below to support me on Patreon. Thanks. Have a good one.